Okay, great. This is recording now. So once again, hello everyone. Happy New Year to every one of you. Um, so it's New Year, but the old habits. Always some problem to delay the starting of the lecture. And so in the last lecture we stopped here. We have shown that the structure constants have totally antisymmetric indices. So basically this if you swap these indices, any two of them, it's an antisymmetric permutation. So you change the sign of the structure constants. So we will discuss very briefly. This is a generic, well-known theorem of in group theory. Is the presence of a Casimir operator, and it's defined by the killing metric in this way, where TA and TJ. Ti and Tj are the generators of the symmetry, and the definition of the Casimir or quadratic Casimir operator is that commutes with all group generators. And this is familiar to you if you didn't learn it before. An example is L squared for SU2, for example. L squared, you can think in terms of OS squared if you are really talking about SU2. So it's the squared of the angular momentum, in this case the spin, that commutes with the three Pauli matrices, and this is something that you are aware of. I will not go into the details of demonstration, but the demonstration is not difficult. Just plugging in the definition of C with TL, and then you just play around with these indices, and you find out that you have the metric here. Sorry, the structure constants showing up. And the trick here is that at the end you have a symmetric operator. So this ij is symmetric tensor. Let's say this object here is also symmetric under interchange of the wall of it interchange of j and m. So change j with m, and this is a symmetric one, but this is totally antisymmetric. So as we have just seen in the previous result, which gives 0. So this proves for any Casimir, by definition, that it commutes with all any of the group generators, as the result is announced here. Right. So let's move on. Let's go to a concrete example. The example of SU2. This is indeed the most important group that we will study. That's why it's worth it first, before going to learning how to do tensor products, which we'll do for generic SUN, but it's important to see the structure of SU2. So in essence, this is a group of 2x2 unitary matrices with unit determinants. And S stands for special, U stands for unitary. And what is special about this? So if it was a unitary group, this definition here would hold, but this condition would not necessarily be there. And a special unitary group is unitary by definition. So the matrices that compose the group are unitary, but the determinant of these matrices is 1. So this is what makes it special, and that's why we call it SU, special unitary groups. So let's look into a generic matrix, and how can we span this group. So take a generic matrix with elements A, B, C, D, and a complex conjugate and transpose it. So you get A, C, B, D conjugated here. And the unitarity condition gives you this following equation here that you can see. Now we equate these things. These are going to be 1, and then you have the off diagonal that you know that need to be 0. So when you pick the off diagonal conditions here, you can rearrange these terms and conclude that A has to be equal to D star and B has to be equal to minus C star. So this is one of the possible arrangements here. And in general, we can write this as a matrix in this way. So now I'm trading A for alpha and B for beta, because it looks nicer because of being Greek letters. But this is the general way we can write a matrix, these 2x2 complex matrices. And now there's another condition, which is the fact that the determinant is unity. So you know the determinant out of here. So this it's the product of this minus the product of these two. So it gives modulus alpha squared plus modulus beta squared. These are complex. Alpha and beta are complex. So the degree of freedom is, in fact, that you have 4 degrees of freedom here, because you have 2 real degrees of freedom for alpha, 2 real degrees of freedom for beta. But now with this definition of the determinant, so you can basically redefine in terms of matrices this what is SU2. So these are the matrices that are of this generic form, with alpha and beta belonging to the set of complex numbers, and such that alpha squared plus beta squared is equal to 1. So this is equivalent to this to the definition here above, to this one here. Right, so each element of SU2 is defined by, and this is what we have observed, 2 complex parameters. So this alpha and beta that we have, so the alpha and beta that belong to C. But then it's subject to one real condition. And this real condition is this condition of the determinant here. And this real condition implies that you can eliminate one of the degrees of freedom here. I think this is, so here, yeah, the string is there. So you can eliminate one of the degrees of freedom here. And at the end, you get 3 independent degrees of freedom. So that's why we have 3 polymatrices to generate this group, which is just a convenient way of generating the SU2 group. And now we can look into this from infinitesimal transformations. So let's consider that these matrices U are expanded about identity, and then you basically expand this condition, the unitarity condition, essentially. You just reorganize your terms here. You get the unitarity here and here, and you conclude from here that this bit here, this has to be 0 with the minus included, of course. So with the minus included, this thing has to be equal to 0. Which is only possible when the T matrices, the generators of the group, T are the generators here, they stand for the generators, when these ones are also unitary. But that's why the polymatrices are unitary. And this is valid. In fact, what we are doing here, this would be valid also for SU3, SU4, any other SUN that you may think of. Just the dimension would change. So the number of free params would not be 3, it would be 4, 5, 6, 7, and so on. So now you can consider again the unit determinant and this condition, doing the same expansion. So now let's see what this means in terms of the T matrices. You may already be guessing if you are thinking about them. So this is to get this, to calculate this, just recall some results. First of all, that the determinant is the product of, so if we consider a certain matrix A with eigenvalues lambda I, we know that the determinant is the product of all the eigenvalues, and also that the trace, because we need this result, the trace is the sum of the eigenvalues. But when you do an expansion about unity, such that the eigenvalues can also be expanded about an arbitrary small epsilon, which are eigenvalues of this x, then the result can be recast in this way. The determinant of A is the product of the eigenvalues, which is 1 plus epsilon, which is equal to 1 plus the sum of epsilon I. And the sum of epsilon I is simply the trace of the matrix X. So we can transpose. We can bring it back to this result here and expand this. So we will have this determinant is equal to 1 by definition of special unitary group. And now when you do 1 plus I the trace of t, because we can put the I out of the trace, but we make the trace of t, this has to be equal to 1. So you see the trace is 0. So the generators of the SU2 symmetry, and by extension of any SUN symmetry, are traceless. One of the conditions is this one, so they are unitary, and the other condition is that they are traceless. So the Lie algebra, now that we have generators, we can define the Lie algebra, and the Lie algebra is given by the generators T that belong to the complex matrices. In the case of SU2 is 2 by 2 matrices, so C2 matrices, such that these matrices are unitary and traceless. So once again, I think this is nothing new. This is just putting in a more mathematical way than what you already know. So we have already seen that a generic T matrix, well, we didn't see, but it's similar to what we have done for the U matrix above. A generic T matrix can be given in terms of some A, B, C, and D, here A, B, C, and D, which is equal to A star, B star, C star, and D star, because of, we know the condition of the unitarity condition. So to make it clearer, let me see, this comes from the fact that T equal to T dagger here. And also we have the tracelessness condition here. So this is because of the trace here. So trace T equal to 0. So if I'm going too fast, please just let me know. So trace is equal to 0. And so you know that the trace is the sum of the diagonal elements. So A plus D equal to A star plus D star. So we can call this X and X star. And when you have this, you know that X is a real number. If X is equal to its conjugate. So it's a real number, or it's self-conjugate. So from here, you can take the condition that A equal to minus D with A and D real. And this indeed, if A equals to minus D, indeed preserves the tracelessness condition, while both A and D being real numbers. For the off-diagonal elements, they are complex in general. So B equals to C dagger, and they are complex. So once again, how many real degrees of freedom we have without a surprise? So we have A and D, which are real, so 2 degrees of freedom, and we have another. Sorry, A equals to minus D. So this is not. This is 1 degree of freedom, and then 2 complex parameters here, which gives 3 real degrees of freedom. And this agrees with what we have found above, essentially. So the most convenient choice for spanning this 2 by 2 matrices under an SU2 symmetry is to choose the Pauli matrices. And you know that the structure of the Pauli matrices is this one. So this is again something familiar to all of you. So the Pauli matrices are the sigma, and the generators is 1/2 of the Pauli matrices. This is indeed like the spin generator. In fact, there are a lot of um, of quantum numbers in particle physics, not space-time symmetries, but behave exactly like spin. We have, for example, the weak isospin, which is what distinguishes an electron from a neutrino. Well, also the electric charge, but I mean at the level of an SU2 symmetry, which is before symmetry breaking. So a left-handed neutrino and a left-handed electron, they belong to the same weak isospin, where typically the neutrino is the one with up weak isospin, and the electron is the same with the down weak isospin. And the same for the muon with the respective neutrino and tau with the respective neutrino. Of course, this translates at the end when you break the SU2 symmetry via the Higgs mechanism. This translates in a different electric charge of both. One becoming zero electric charge, the other one becoming 1/2. So just to give you an example here, let me just write down here a quick example of this. For example, typically you can write L, which is a doublet, where you have the neutrino here, so electron neutrino, and left electron, let's say. And this also has, so this is an SU2 doublet. Also, there is another thing, another quantum number that is hypercharged, which is equal to 1 or 1/2, it depends, or minus 1/2. Let's put minus 1/2, and the electric charge at the end will be equal to T3 minus the hypercharge here, and T3 is the weak isospin component. So T3 of nu E is equal to 1/2, and T3 of EL is equal to minus 1/2, because it's so this is the down component and the neutrino is the up component. And you see, when you sum, you go into the definition of the electric charge, it gives 0. So it gives basically 0 in the neutrino and gives 1, it's minus 1 in the lower component. So sometimes it's also defined with y/2. Here, let me put it in a different color. Sometimes you see this, but also here you have to multiply by 2, and the hypercharge would be minus 1. It's a matter of convention. Right. Okay. This is just a small taste of what we are going to learn further below, and why the importance of, in this particular case, of SU2. Okay, so these are the Pauling matrices. You see they are clearly traceless, all of them, and they are unitary as you know it. Okay, so there are a few commutation and anti-commutation relations among the Pauling matrices. So this is a well-known commutation relation. This is also another well-known anti-commutation relation. And also these results can be obtained from these conditions. And of course, you can now translate it into the generators of the SU2 symmetry, which is 1/2 of sigma. So essentially, the commutator is just putting 1/4 outside and yielding this result, from where you identify with the definitions above for the structure constants. You realize that the epsilon tensor, the Levi-Civita tensor, epsilon I, jk, are the SU2 structure constants. Right. There is also, let me just say something. I have uploaded these notes in my Google Drive for you to. Some of you asked to get these the notes before, so that you can follow and take notes. Maybe it was a bit too late when I when I remembered to do that, but if you have the opportunity to print it out, you can also do that way. Follow the lecture and take notes on your own. I hope it works at least for the next lectures. I will try not to forget this time, as I put it too late. Anyway, so let's now look into the normalization of these SU2 generators. What is the conventional normalization? So for that, let's first take the trace. And we know, again, the trace is given by the trace of the product of two polymatrices, the trace of the product of two of the generators. You can use the known results that were put here above. I believe that all of you have learned this in your quantum mechanics course a few years ago already. Maybe not before that, but at least the first quantum mechanics course, this typically shows up. And now you just make use of the properties of the polymatrices in the particular case for the second term, that they are traceless. So this term goes away, and you are left with just the first term, but you also know what is a trace of the identity. In this case, of course, it's a 2 times 2 identity. So that's why you get these two here, and the normalization comes in the usual way, that you see here. Right? Yeah, and this is the killing metric. So from the definition of the killing metric above, here, this is the definition of the killing metric. You also can obtain the killing metric of SU2. And there is one result here that will classify also this type of group according to some of the definitions and theorems that we have introduced in the first lecture, quite 3 weeks ago, I guess, already. So it was a long time. May help us forgetting a bit of what was mentioned there. But you have use the killing metric following the definition, and you realize that this is equal to Ij. And from a second theorem, the theorem number 2, we note that from the SU2 algebra, we have this condition here, where A is the SU2 algebra and X. So these are generators of A. Exactly. So the key point here is just to prove, or is just to show that the SU2 algebra does not contain a proper ideal. And in fact, we had a discussion with Osvaldo actively in the last lecture, where we have understood that SU2 does not have an ideal or proper ideal. Thus, the SU2 algebra is simple. And this is the result of theorem 2, is that if a group does not contain, or algebra in this case does not contain a proper ideal, then the algebra is simple. And that's why we say, you may have heard a few times that SUN groups are simple groups, not because they are simple to handle, but because this is the mathematical definition of the algebra that generates them. Okay, good. So we have seen that the polymatrices define the fundamental representation. Well, we didn't see. I'm now telling you that the polymatrices define the fundamental representation of SU2 because they act in two-dimensional vectors. Let's say this is kind of an abuse of notation. Let me put here some quotation marks. Which are denoted as SU2 doublets. So when I mentioned above a doublet made out of a neutrino and an electron, was this what I was meaning? So in general, in pure mathematical terms, so you have a doublet that you can write as a 2. Typically, this is even, to standardize our notation a bit, this is typically written as a boldface number, a representation of symmetry. It's a boldface number, and it has two components, which are complex numbers, and the polymatrices written in the form above, in this form here. You see they are 2 by 2 matrices here, so they act on this they act on the generator, sorry, on the doublets, because they are 2 by 2, they have the correct dimension. Or what I want to say is that the indices of these polymatrices, so you can you have here like AB indices, and these AB indices run from 1 to 2. So basically they are fundamental indices. So I mean fundamental because, or doublet indices, let's say. Let's not say fundamental just for now. They are doublet indices here. So doublet because they only go from 1 to 2. And this is the dimension of a doublet. It has 2 dimensions, 1 and 2 here. So, yeah, this defines, yes, this defines the fundamental representation, exactly. So this is what I start by saying, that the polymatrices define the fundamental representation in this way. And what about the adjoint representation that we have already mentioned above? Now I recall that we mentioned in the previous lecture. So the adjoint representation, we have seen that in general, the generators are given in this way. And basically equal to minus IF IJK. For the case of SU2, all that we have to do is to replace I, so F by epsilon IJK, where we know that I, J, and K run from 1, 2, and 3. Now, these are no longer the doublet indices, but these are the indices that identify a polymatrix. So we have 3 polymatrices. So I can write down here. So IJK, 1, 2, 3, run from 1, 2, and 3. So this is because we have 3 polymatrices. That's why the dimension, the dimension of these matrices in the adjoint representation is 3 by 3 and not 2 by 2. And from this definition, so basically the generators of the symmetry expressed in the adjoint representation is given in this way, as you can see here. So T1, T2, and T3 is given here. Right. Another important definition is to look, and this is a special case of among every SUN, something that happens to the best of my knowledge only in SU2, which is the complex conjugate, or also known as anti-fundamental representation. In fact, I prefer to use anti-fundamental representation because it's more, I can relate that anti to anti-particle. Anyway, because at the end of the day, we want to describe the world of particles with these objects. So, using again this definition with R's, in other books, in other references, people also use these. But here, so you have the fundamental representation, which we can rewrite in this way: e to the power of t in this simplified notation, where t is basically it gathers together, so the polymatrices and some omega ij, where this omega are. This is equivalent to the when we had previously done this transformation of a field. Phi goes to phi prime equal to e to the minus e alpha. Let me not use the minus here. I say some charge alpha. So in fact, what's going on here, and let me not put the charge to remove some confusion. Just to imagine that the charge is 1. So we have this alpha, and we can also write here identity, because this can be a transformation of, say, phi can be a vector, so phi can be something like this. Phi 1, something, phi n, this is something that can happen. And if you're talking about a U1 symmetry, we can have this this identity here. So the correspondence here is that these omegas correspond to these alphas, and of course the identity corresponds to here to the polymatrices in the case of SU2. So this is what we are doing here, the way of representing the representation. For the complex conjugate or anti-fundamental one, we simply complex conjugate it, and so this is the definition. And now let's look at some examples. First, the transformation of a doublet. So a doublet here that goes to psi I prime, and this is what in fact I was saying here above, but for SU2. So the transformation is given in terms of a matrix U ij. So this j is summed up with that j there. And you can write this in terms, and now this is the actual one-to-one correspondence to what I was writing here. So this phi prime is this psi prime, and the exponential comes here, and the indices are here to be matched. So this is in fact, so you see you have three polymatrices. So this omega A runs from 1 to 3, and ij, so I should write it here. So it's equal to 1, 2, and 3, and ij equal 1, 2 only because it's a doublet, while A is identifies the generator, and we have 3 generators, and has the dimension of the adjoint representation here. For the case of an anti-doublet, so we just let's just conjugate this thing here. So we have this uij here. I believe there is a conjugation missing here. There's uij here. Then we have this psi bar j, and what we have to do is to put a minus here, of course, and conjugating these sigmas. Also, omega, this omega real, and actually, this is, I remember that João Novo asked this in the previous lecture about something similar, and these omegas are real parameters. So that's why you can write this. Right, so far so good. So an SU2 doublet transforms in the fundamental representation that we have seen. Also, we also have triplets of SU2, and in fact triplets are 3 by 3 matrices, because they transform in the adjoint representation. So here, this is this sigma. This is not a sum. This is a triplet. It's typically denoted as sigma when we are talking about the SU2 triplets. And this is a 3 by 3 matrix. And in fact, so we have the generators in this case, the transformation law is also a 3 by 3 matrix, and you have the indices. So these I and J are the free indices, and then you have this kappa and this L that are contracted among here. But this is just to introduce the triplet. But back to the anti-fundamental representation. Back to the anti-fundamental representation, which we have seen, using a result that you know. So you have used this result several times well, at least all of you that did the standard model 1 lectures in the last and in exercise 2 and also 1 there, this result was there to be derived. And you can just note the following. You can just note this result. So you just expand this. And you conclude that this minus I omega A sigma A star equals to T star. So this is to plug the result here. So now we can put that result here in this exponential. There you go. So you put this sigma 2 T sigma 2. And because of also the unitarity character of this sigma 2, you can write this in this way. And now recalling, so this is just a bit of math. Now this is just an auxiliary calculation. when you have an exponential with the three matrices, and this is what you have here, you have three matrices here on top of this form, you can write this in exponential form, expand the numerator, and because of the unitarity of these matrices, you can remove all these intermediate parts where you have identities, such that this is equal to a b to the power of n times a minus 1, which is what you get. So you get several b's here and a's and a minus 1s, the inverse of a, also several times that you can remove because it's identity. And then plugging it in the exponential, you get also a well-known result. So this is a possible, this is a known result. So you can make use of this result to the case of the complex conjugate representation, where you have the sigma 2 times sigma 2 minus 1 here, and obtain this result here. And what is important about this result? So the first observation is that the fundamental representation, because this here inside is the fundamental, the importance is that relating the anti-fundamental representation with the fundamental representation. And the first observation is that the fundamental representation and its complex conjugate, that is the fundamental and the anti-fundamental, are related by a unitary transformation in this way. So R star is equal to S, R S minus 1, where S is unitary. Now there are two definitions, two important definitions, which is, what is the definition of a real representation? So a representation is real of a certain group if it's equivalent, if it's going via a unitary transformation to R star in this way. S RU S minus 1 is equal to R star. This defines a real representation. But there is another definition that says that a representation RU is said to be pseudo-real if S is antisymmetric. And this is the case of sigma 2, which is what we are using, which is both unitary and antisymmetric. Then the anti-fundamental representation of SU2 is pseudo-real. So that's why, and this is particular to SU2. In SU2, so you can write doublets, like I will write already like this. You have a doublet, and the doublet is equal to its adjoint doublet, or the complex conjugated doublet. But for example, in SU3, the fundamental representation of SU3 so is a triplet. So this is for SU2. Let me just identify that this is for SU2. But if you are talking, for example, about SU, let me even put any SUN. So in general, the fundamental representation, which has the dimension of the group, is different than the n dagger here for n bigger than 2. So this is a particular case of SU2. Right, so we have came across most of the important definitions of the SU2 group. So its structure, we have looked into its structure, but we are now going to look into a broader perspective to it. Basically going to the case of SUN groups. But first of all, is there any question, anything that you want to ask? Right.
Yes, I didn't understand the conclusion that SU2 is simple.
That's just up to, you just have to go above and check the theorems that we have defined above. So let's first, so to get that, I think so. Who spoke? Fernando or Etevaldo?
Fernando.
Fernando. Okay. It's just because I like to know who I'm talking to. Right. So let's see above. So this is something that you can check. Let me see if I find it here. So it's completely symmetric. Now this is already what we have seen. Okay. So I also have to recall myself of these definitions. So this is something that we discussed last lecture, that the solve-algebra is an ideal under these circumstances here. So A is a solve-algebra of LG. And if we have this relation, so if any x belonging to A, if it commutes with any z that you know belongs to L, so the bigger algebra, and if the result of this commutation gives something in A, so in the subalgebra, then the subalgebra is an ideal, and it's a proper ideal if this is not a trivial relation, if A is not the same as LG. So this is the definition of a proper ideal and a proper group. Now, another definition is a Lie algebra is simple if it does not contain any proper ideals, and semi-simple if it does not contain a billion ideals except the null element. So this is a definition. And so what we did down there was checking this condition for SU2. So recall that the algebra is simple if it does not contain any proper ideals. And what are proper ideals? Is an ideal under this circumstance where A is not equal to L. So now let's go below again to SU2. So we have this in mind. So this was here. There we go. From the SU2 algebra, so we have the SU2 generators. Exactly.
Sorry, I can't hear you.
Yeah, sorry. Sound just died.
Can you guys hear me?
Yeah.
Okay. So it's better now. So I think this, okay, people are saying yes. Now I'm using my tablet's basically fronts. Let me try to do something. This is recording, I guess. So you let me check if this is really recording. Yes, this is recording. Right. So let me try to share the screen again. So now I'm the host in the tablet, and I will not waste more time. So can you see the?
Yeah. Everything's fine.
Is anybody not seeing the screen? Guys, can you say something, because it's frozen in my computer?
We see the screen. Maybe if you can you move it, or
let me.
So I'm still seeing the ideal, or the statement that SU2 is simple. Okay. Is
it moving?
It's moving.
Right. So let me. I'm just having a trouble in my laptop. Let me force quit that one. Okay. While so since this is recording here, I will just for a moment keep on. So first of all, Fernando, did you where did you stop hearing me? Fernando?
I think you're beginning to talk about the case of yes, SU2.
So I was above, so I was starting to talk here. Let me see. Let me go back again to this here. So this is what I was showing. Let me try to connect it again in my laptop, just because it would make things a little bit simpler here. But this is this that is on the screen now is what I was telling you, that we have for two generic algebras, we have some algebra A and some algebra LG, where the generators of A, when they commute with generators of Z that are the generators of LG, it gives something that is contained in the algebra A, and we say that A is a proper ideal if, in addition, we have A different than LG or the zero element. So this is like when it's not a trivial group or a trivial correspondence between A and the LG. This defines a proper ideal. Now, if and then there is this sentence that was problematic in the last section, the discussion. But then there is this definition that the Lie algebra is simple if it does not contain any proper ideals, or semi-simple if it does not contain a billion ideals, except zero. But the thing is, let's concentrate on the simple algebra case. So a Lie algebra is simple if it does not contain proper ideals. What is a proper ideal again? So we come here, and we need to have like a commutation between two generators of an algebra A and an algebra LG. And if A is not the same as LG, then it's a proper ideal. If you don't find this, if, for example, A is equal to LG, if the only way of getting this condition is that A equals to LG, then it does not contain an ideal and a proper ideal, and the algebra is simple. Right? So this is the definition. Now let's look to the case of SU2 that we were discussing. SU1 groups, SU2, where is the simplicity defined? I guess it's here, exactly. So again, so this is the definition that from theorem 2. I mean, this is a result from theorem 2. But for SU2, so the X and Z, so what we can have for X and Z is only the polymatrices. And this makes A equal to LG, which is in fact L, so the algebra that generates SU2. And because of the definition below theorem 2, we can say that the SU2 algebra does not contain a proper ideal, and therefore it's simple. A simple algebra. Is it now clearer, Fernando?
But why does X and Z need to be can only be the polymatrices? Isn't there any other?
There can be, so the polymatrix is the most convenient choice. You can have something different that is not as neat or as easy to visualize as the polymatrices, but this will always be obeyed because it's only up to a rotation of the polymatrices itself. So you can pick up the polymatrices. It's like you can think of the polymatrices as if you're thinking like a R3 space, for example, and you have the 1 0 0 0 1 0 and 0 0 1 versors, like the unit vectors. You can think of the polymatrices as the unit vectors of SU2, and the most convenient way of writing them is in the way that you know it. But you can like make the axis of this symmetry slightly more complicated, and they don't have to look like the polymatrices that we know in the familiar form.
So, correct me if I'm wrong, another way you could represent SU2 is with quaternions, correct?
I think so.
So you could do that because they map to S3, which is a one-to-one map to SU2.
But that's an isomorphism, I guess, if I'm also not wrong. That there is an isomorphic isomorphism relation between, because the SU3 and SU2 are isomorphic groups, that they are not the same.
The relations between the bases of the quaternions and the IJK and the sigma matrices are exactly the same, right? So
yes, they are exactly the same.
Yeah.
And the point here,
the screen just stopped sharing.
Oh, bloody hell. Let me put it again. She's being a bit problematic today in terms of screens. So can you see the screen now?
Yeah, everything's fine.
Okay, right. So yeah, but the point is exactly that. So you here, Fernando, even if it's not the polymatrices, this result is always the same. You would generate the SU2 algebra with 3 other matrices, and those so the A and the LG are always the same for the case of SU2 that we are studying here. So for that reason, this is why SU2. This is a rigid result. Let's say it's a simple group, because you can. It's just up to a matter. Once again, repeat myself to try to be as clear as possible in the sense that if you define something else, as Osvaldo was saying, it could be that you have something that are not the polymatrices, but either you map the polymatrices to that something else, if you go through something like quaternions and so on, or you write the polymatrices in a completely different way. Basically, their components would not be as illuminating as they are when you look at them now, but this would be the same. The commutation relation between them would always fall inside SU2. Is it clear, Fernando?
So it's independent of the representation. That's what you're saying.
Let's see. What I'm talking about is not exactly the representation per se, but the way these matrices are written. But yes, it's independent. You can think of the choice of axis, of the choice of basis. It's independent of the choice of basis, basically. This result. It's better said in that way.
Okay, thanks.
Okay, very good, very good. And yeah, please, guys, ask questions if you want. Okay, let me see. My computer is back to life. Let me try to just do this. No, I don't want to stop the sharing. Let me just do the following things. So I would like to Can you guys hear me again?
Yeah.
Yes.
Okay, good. So let's try this way again. Right. So let's move on then. So seen this. Okay, SUN groups. Let's start discussing SUN groups. And there you go. So SUN groups. What are they? They are the so-called special unitary groups. This is recording, right? I guess let me just check if this is recording. Yes, it's recording. Sorry, I just wanted to confirm. So special unitary groups. So they are unitary and special unitary. So this is what we have seen. So they are the generators of the group are unitary. T equals to T dagger, and the determinant of these generators is 0. Once again, let me tell you, Fernando. So whatever you choose for your generators, even if it's not the polymatrices, they have to obey this condition, this unitarity and oh, bloody hell, this unitarity and.
Sorry, the screen stopped sharing again.
Yes, that's why I said bloody hell, because I noticed that. This is going to be a fight today. That's why I wanted to have the computer in front of me, because I can follow faster what's going on if I'm not only relying on my tablet. Right. Okay. So continuing, and these groups are very important for particle physics because they constitute the basis for the global and gauge symmetries upon which the standard model and also its extensions are built. Of course, there are other groups like SON and the exceptional groups, symplectic groups. So it's all a big classification for groups. But the most fundamental ones, the ones that are most broadly used, are the SUN groups. SONs are also sometimes used, but it's not. These are spinorial groups. The generators are basically the generalization of gamma matrices, like a generalization of a Clifford algebra. And also the exceptional groups. I like to work with exceptional groups, but they are a bit more complicated. But they are good in the context of grand unified series and these sort of things. So, but in general, so for a UN group, a unitary group is a group in CN, so where you have the general linear transformation of n by n matrices that are unitary. And the special character is if also we have determinant equal to 1. So the matrices belong to UN, so the above condition, or the above groups, and also the determinant is 1. Right. So now you can see from here, from taking the unitary from this unitarity condition, that the determinant in fact can be equal to plus or minus 1. This is because you get this condition when you evolve this. And I'm just wondering why was this condition put here. Maybe I will remember. So our focus will be in SUN groups. Yeah, exactly. Now I remember. It's just to say that when you have unitary matrices, you can have a determinant can be either plus or minus 1. But for unitary groups, is those that the determinant is 1, not the minus 1. So that's why I say the focus here is on SUN groups. So this is all generalizing the previous case of SU2. So we have a set of complex matrices. So the generators are a set of complex matrices, n by n complex matrices, under the same circumstances. So they are unitary and traceless. And how many degrees of freedom do we have in these matrices? So think of n times n matrices. These matrices are complex. So each element is a complex number, which if you assume that all of them are independent, we have 2n squared real degrees of freedom. So basically you can just count, you can look to the case of the 3 by 3, 4 by 4, and so on matrix, and you can realize this 2n squared. Now, from the hermicity of the generators, yeah, exactly. This is something that I should say better, that I've been saying unitary today. Yes, they are, but here T equals to T star is that they are hermetic, these operators. And the same in SU2. I think I've been saying unitary all the way through, but this is, in rigor, this is what I want to say. They are Hermitian operators. So this hermicity condition imposes n squared constraints. You can convince yourself by looking at these such two generic matrices. So we have, so the diagonal elements have to be equal. So AII equals to AII star. And for the off-diagonal elements, you need to have this condition. So basically, this one has to be equal to that. So by flipping the indices. So Aij has to be equal to the conjugate of Aji. And this, if you count the number of indices here, this gives rise to n squared constraints, basically. So we already have, and we have another condition, the tracelessness condition, that puts one more constraint. So you take that the diagonal elements, these diagonal elements, you sum all of them, and this is 0. So you can eliminate one of them with this condition. And by doing so, we have the 2n squared, the total freedom that we set in the beginning, 2n squared, minus the n squared coming from the hermicity, and minus 1 coming from the tracelessness condition. So this n squared is coming from this is from T star equal to T, and this one is coming from basically the tracelessness condition. So overall, we get n squared minus 1 degrees of freedom. This is essentially what we are. And this is also, by coincidence, well, not by coincidence, this is in fact the dimension of the Lie algebra and of the adjoint representation. Right? So the freedom that we have in SUN matrices gives you the dimension of the corresponding Lie algebra and also of the adjoint representation of such a group. Now, irreducible representations. So these representations of SUN are given in terms of tensor fields that transform under SUN in different ways. So in SUN, you can have an object psi with several indices. And the transformation laws are given by the representations of SUN. Depending on which representation you are, if, for example, SU2, you can have singlet, you can have doublet, you can have triplet. So basically, a singlet is in an invariant of the symmetry. No matter what you do to your SU2, no matter you rotate it, it's always the same. It's invariant under rotations of SU2. A doublet of SU2 rotates has a doublet. So basically, you know how to rotate it, you know how to transform it, you know how to use the polymatrices to make transformations on that, and to generate a generic rotation, let's say. A triplet transforms in the unjoint representation, so it transforms differently. So you already, in terms of tensors, the first has one index that goes from 1 to 2, and the second, the adjoint, has two indices, as we have seen above, each one of them going from 1 to 3. So the fundamental representation, which we typically represent by n and has dimension n, is given in terms of this. We always write, so we are going to define the representations, so the fundamental representation in terms of a psi with an A on top, like this. And the transformation properties, so this is the invariance. So once again, so if I ask you to check if a Lagrangian is invariant under a certain SUN symmetry, what you do is this transformation property, of course, by knowing which SUN we are talking about, and therefore by knowing what are these U matrices. But in this generic case, you have U goes, so psi A goes to psi A prime, and there is a unitary transformation, AB, and so this B is contracted here, and B equals from 1 to n. So these are n by n matrices, and of course they belong to SUN. Now the complex conjugate representation, or the anti-fundamental representation that we have defined. So we typically define with n bar, as I have already mentioned above. And let me be even more, a little bit more precise here, and use like boldface notation here, and boldface notation here as well. This is how it's usually represented. So the complex conjugate representation basically transforms in a complex conjugated way. So now here we will define the complex conjugate representations with the indices like in the lower part of the field. So the fundamental indices are upwards, and anti-fundamental indices are lowered. So this is something that we will use. And we always know, if we're talking about fundamental or anti-fundamental indices, whether you look at them and see if they are either up, fundamental, or down, anti-fundamental. This is, some authors do the opposite, but this is the way I usually work, so I prefer to keep my my way of treating things. So this transforms in a very similar way, but now we have the complex elements of this matrix, and also the B is here below. This is so far this fundamental representation and complex conjugate representation. These are the most trivial, well, not counting the singlet representation, which does not have an index, or it contains several indices that are all contracted among themselves. So basically a transformation is given, so a non-singlet, something that is not a singlet, is given by the number of free indices or indices that are not contracted upon. But in general, we can have a tensor representation, n by n, so np by n bar q. So here, 1n stands for the, basically here it's for the fundamental indices, and the other one, n bar, will stand for the anti-fundamental indices. And P and Q don't have to be the same number. You can have, so here you have P fundamental indices and Q anti-fundamental indices in this tensor representation. For example, I mentioned above for SU2, what I wrote above for SU2. Let me put here a side notes. So we have seen a doublet. We have seen a doublet that has one index, one fundamental index that is the same as anti-fundamental. So in fact, for example, in SU2, we have seen like something that is psi I with I equals to 1 and 2, and we also have look into like a sigma ij, which is a triplet, and this has one. Let's say this is a little bit abuse of language, but this is a fundamental and an anti-fundamental. Because of being a pseudo-real, the anti-fundamental is not really anti-fundamental in SU2. They are equivalent. It's a pseudo-real representation. But you can think of this in general. You can think in this way. And this is a tensor representation. It would be a n by n bar representation. And of course, to make sure that this belongs, it's an invariant of the group, you need to know how does it transform. And now, instead of having only one matrix for the anti-fundamental indices, you have Q matrices. So these here are Q matrices. Q matrices. And you have, for the fundamental indices, you have P matrices. And also the indices here. So the anti-fundamental are in this way. And the fundamental one are like the opposite way. So you see here. So I'm writing everything here. So there is nothing special here. But this is the way it transforms to a certain psi prime, a certain psi prime, which would have different indices here, basically. So this is what defines a tensor representation. And what about invariant tensors of SU2? So one of the invariant tensors of SU2 is the generalized Kronecker delta and the Levi-Civita tensors. So how do we see that these are invariant tensors of the symmetry? And this is very useful because then you can use this, both the delta and the epsilon tensors, to build from the fundamental representation to build, or from other representations even, to build further group representations. Because as it is shown here, the delta, if A and B are indices of a certain SUN, you know how does delta transforms. One A is fundamental, the B is anti-fundamental. So delta always relates a fundamental and an anti-fundamental index. I should write here that it relates fundamental with an anti index. This is just to make things here more concrete. So, and you know how this transforms from the above definitions. So here you have CD, and now you know that you can act this delta on one of the U's. So let's pick this D, which will become C. So it's C here. And now you know, because these are unitary matrices, you know, so you have C here contracting, and you have A and B outside. This is a unitary matrix, so you know this is delta AB. So this proves why delta is an invariant tensor. Although it has 2 free indices, this is invariant of the SUN symmetry. Epsilon is also an invariant, but epsilon does not relate fundamental with anti-fundamental. It's either all fundamental or all anti-fundamental. And this is why, in this sense, so I tend to, in most of the cases, unless it's not important, but why I use typically epsilon with indices always on top or always on bottom, because that matters in terms of understanding whether they are fundamental or anti-fundamental. This is why in the previous lecture I said, look, sometimes here with epsilon's summation, so the Einstein convention will not be possible to hold. I mean, it's there, the summation. It's just the indices are not one on top and one below, because there is another thing that basically overshoots that, or it's has a bit more weight. And that is, I want to look into the epsilon and know if the indices are fundamental or anti-fundamental. And that obliges me to keep all of them either above, on top, I mean, or below. And in this case, let's look to epsilon with all fundamental indices. So here we use U's without U star.
Sorry, I want to clear it up. So we're still using the summation convention, but only, but not if they're mixed indices, or what's going on?
So we use the summation convention.
If they're mixed indices, we don't sum.
What do you mean by mixed indices?
So if we have like A, like A at the top and A at the bottom, we don't sum over the indices, or do we still?
They do. They still sum. Let's okay. Thank you for asking. So that this gets clear. Whenever indices are on top, so A up and on top and below, BB, CC, DD, and so on, we always sum. Here it's always being summed. So C is being summed with C, and here with epsilon, so B is being summed with B, Bn with Bn. This is all the Einstein summation convention. The thing is, sometimes you have things that I will put here on the screen. I just have to find, I think it was somewhere around here. It's where the structure constants shown up for the first time, I guess. So we had this FABC, A and B here are being summed, but then you have this gamma C here below. I'm not now going to judge if this C should be above or below, but the thing here is the following. I think here it's where it matters, I guess. So here we have like indices, all of them on top. So here we are saying that these are fundamental indices. But X also, it has fundamental and fundamental, two fundamental indices here. And here C is also being summed over, but one is not on top and below. So the thing is, repeated indices, the repeated indices are being summed over. So the Einstein summation convention always holds. But sometimes repeated indices, they are also being summed. You see, Oswald?
Okay. So it's the same that we've been doing.
Yeah, the same that we have been doing.
Yeah, it was just because you made the comment on it. I was wondering if something had changed or something. But yeah, okay,
no,
it's fine then.
Nothing changed. It's the way that we have been doing. The thing is, whenever we can, we will put indices above and below to use the Einstein summation convention, and you can do that in your exercises. That's something that you can do. But some other times we will not be able to lower an index because we are going to be using fundamental and anti-fundamental. But this depends on the particular case that we will be studying, and we need to judge case by case. In fact. I mean, when you are doing some calculation, you need to check whether this holds or not. But when one is on top and the other one above, it's summed, and the repeated indices, of course, as it's happening here. Okay, the epsilon. Right. Now let's see that epsilon, and this is a very important result, and you will also use some of the things in your exercise, the exercise that I'm going to prepare for you. I already prepared a few, but not all. But this is something that will be also important in building Lagrangians. So if you have for this use, so you know these are fundamental indices, so they transform with the U matrix, not the U star from the definitions above. And here you have epsilon with B's, fundamental indices. Now you just expand the U's about the unit matrix, and you get this chain of matrices here, which gives you like the product of several deltas, so which is taking the first component, and a product of deltas and the t's, so one t and various deltas, and so on, and so on. But the thing is, here we are only keeping terms up to first order in t. So let me terms up to first order in t. Right, so with this in mind, so we have these terms up to first order in t, we get this expansion, and this is first order, this is first order in t, so only one t here, and the indices should all be carefully written. And now you start contracting this this epsilon with the corresponding things. And so the first one, it's the B1 index contracting here, and so on. And the last one is, of course, the first one with deltas, with a sequence of deltas, becomes the epsilon A1 AN, the original one. And then we have a sum of t's times some epsilon, where only one index is different. Only one index is basically summed. Here it's the last one, here is the first one. But we know that these epsilons are only non-zero when B1, in this case, when B1 is equal to A1, because then you have A2, A3, A4, and so on, AN. So if B1 is equal to A2, the epsilon is going to be 0. And the same here, if Bn is equal to A10 or An minus 3 or N2 or whatever, this is going also to be 0. So this, we need to make all of this with A1 here. So basically the epsilon will capture the remaining, so the only one that doesn't give a 0 here, which also tells us that we need to rewrite the same in the generator. And now you see what's going to happen. So you have here A1 A1, AN AN. You can put now epsilon A1 AN outside here in evidence, and you get something which is the identity, or 1, sorry, this is plus I, all of this, which is the trace. This is the definition of the trace that you have here. And by definition of SUN, the trace is 0. And therefore, we have just proven that the epsilon tensor is also any generalized epsilon tensor from epsilon ij with 2 indices up to epsilon A1 AN with n indices is an invariant of the corresponding n-dimensional SUN symmetry. So this is very useful because you can build Lagrangians with deltas and epsilons, knowing that you are not ruining the invariance properties that you build. It's not because of an epsilon or a delta that you will explicitly break a certain symmetry, or if you'll induce some forbidden term in your Lagrangian. So you can really use these indices. Okay, so I would say to make a short break. What do you guys think? In fact, I'm fine to continue, but I guess that you may need a break to refresh your mind a little bit. What do you say?
Yeah, sure. I think it's a good idea.
Okay, so let's have a short break, because we are going to discuss now things. Now from here onwards, it's going to be with indices, and we are going into the Young Tableau and for that we need this. I want you to be fresh. So okay, so let's give us 10 minutes and resume exactly in 10 minutes from now at 11:49. Okay, I will pause the. Let me pause here the recording. Yeah, agora não. Agora não. I have an intruder here. Há muita gente aqui, Guilherme. Vai lá para dentro. Oh, and this is okay. So it's recording again. Okay. By the way, if some of you, so actually Alexandre sent me an email. I read the email yesterday, and of course we can talk, but let's not use this the time of this lecture. We talk, and this is valid for all of you for the SM1 course. If you have any questions about the take-home exam that you want to ask, I mean, I cannot solve for you it, of course, but I can tell you what's the idea. I can clarify a few things. Okay, this stopped recording. Not recording, but stopped sharing the screen. Not in a good time. Let's see if it shares. I guess it's sharing again. Yeah, and also try not to leave that take-home exam to the last days, because it's important that you have enough time to do that, and and also to think. To some of you, I made comments in the previous that a few more details were needed in some questions here and there, and I want you to.
Yeah, so I actually found that really funny, because I've been hearing that since middle school. I remember my math teacher in like 7th grade, and she would always, from 7th to 9th grade, she would always tell me I need to show all the calculations. I would always skip them.
Exactly, and
it's a problem.
It's a problem. I can tell you why. It's not. If you notice the marks, the discount was small. It's like every time there was something, you take 0.1 off. So it's not a remarkable thing. And here, I also believe you don't have the pressure of the marks, but of course, it's good to do as best as possible. That's something that if you do that, it's a professional thing to do that, and even if you don't need to get into, you already have, most of you, PhD scholarships and so on. But it's good to not take this in a sportive way. Let's say it's good for your learning. It's good as an attitude towards what you to value yourselves. So
see, that's the sad thing. That was me trying.
But the thing is, so I didn't want to say that it was you as well, but everyone understood now that that you were one of those targets. But the thing is, Oswald, and for everyone else that sometimes skip details, is that, of course, sometimes you may write something very obvious. Also, you're not going to reinvent the wheel. You are not going to say, okay, 1 + 1 is equal to 2, and because of that there are various theorems and axioms. No, you don't have to do that. You need to judge what is reasonable. This is also an art, let's say, in this way, what is reasonable. But the calculation details should all be there, because sometimes you have different ways of. I found different solutions than what I would have done, and were still correct, exactly correct in the same way. And you, Oswald, were on one of those cases. You had some solutions.
Yeah, so there was one, for example, that I meant to ask, if we're talking about it. So when we do the, I think it's in exercise 2 of the second hand, in where we do the transposition of the spinner. And I didn't really see. You mentioned that I needed to show that the row version of the spinner is of the spin, the original spinner is phi or psi and chi bar. And then you said I had to show that the row spinner would be psi dagger and chi transverse because it's already been conjugated. I don't see how I would show that other than just the very definition of it.
Yeah, we can see that later. I need to remind
Okay,
myself
yeah.
exactly what was the put in that way. It seems not to be a big deal, but I need to look into the.
Yeah. Okay. Sure. We can talk. It doesn't need
we
either after class or we can meet up at some
Yes.
point.
Yes, we can meet after this class. It's not going to be very easy for me.
Yeah, we can set something up.
We can
just to look over some
do
of
that.
these things.
We can
Okay.
definitely do that. But anyway, so the point is that sometimes there are results that are not obvious, or you do it in a different way, and it's really hard sometimes for me. So because it's not only one person, it's in this case it was 7 and now it will be 8, solving things and potentially in each one having a different way than between themselves and different than mine. Well, it doesn't happen often, but it can happen. So if I have to think if you don't show the details and I have to think about the details at every single step, it will be a very lengthy thing and tiring, you see. And also, I may not understand something, and you may get less points because of my lack of understanding of something. So if you explain, I'm doing this because of that, then it makes the step a lot smoother. And that's also important when you're writing a scientific paper. In a scientific paper, you don't put the full calculations, but you do explain what's going on and what you do, or referring to known results. So it's a good practice to have everything organized in that way. That's why also in the take-home exam I wrote that you should show all the details and so on. Anyway, guys, I didn't want to waste more time. This is not wasted, but I didn't want to spend more time on this. And let's go back to the group theory. And okay, we have already we have shown just in the previous lecture, in the previous hours, that we have invariant tensors, epsilon and delta. And this is something that is demonstrated here. So now we can use these invariants, these invariant tensors, to build new tensors, as I said. For example, imagine that you have a certain tensor which has p 2 times p, let's say c1 cp and d1 dp. So p fundamental indices and p anti-fundamental indices. Now you can build an invariant of the theory, so one where you have all equal indices, a singlet. This is a singlet of the theory, in fact, just by stacking in front of psi p deltas. So this is one of the possibilities. Okay, let's build a singlet with deltas. So in this way, you can build a singlet of the in the Lagrangian. This could be a term in the Lagrangian with only one field. This is already a singlet. So your Lagrangian could be equal to this psi. And this is an invariant of SUN, as it's shown here. So A1, AP. So you make this goes to some prime, A1, AP. And now we do we put for the anti-fundamental indices, the matrices which start. So P matrices here, other P matrices there for the fundamental indices. So with the fundamental transformation here. And now we can organize them. So this complex conjugation, it's like you have dagger, and then you flip basically the order. So D comes inside and A comes to the left, and the other one goes to the right. And you now can contract this, and you know that this is a delta, and a lot of other deltas here. So once again, you have a lot of deltas stacked here in front of someone that is C1 CP and D1 DP. which is in fact, and because the indices are dummy, you can write this as A1AP, A1AP. And here you have proven that this term is in fact an invariant of the theory. A tensor, like, it's not a tensor, it's a singlet, but written with P fundamental and P anti-fundamental indices. In rigor, these indices are contracted upon. So another SUN invariant can be, you have like a fundamental, so a tensor with the n fundamental indices here, and you can contract with one of the invariants of the group, another one, which is the epsilon, but now epsilon having anti-fundamental indices here. So you do this and you can prove that this is indeed an invariant. So you do the same thing with the epsilon, and then you put the u's, which stand for the psi prime. So you know that epsilon is equal to epsilon prime, as we have verified here. It's an invariant, so we no longer need to bother ourselves in putting the primes on epsilon. So here we don't put the epsilon prime here because it's already proven above, but we have to put the prime on this psi. Now you put the U transformations on the psi, and you relabel here the indices, and you get something again which has the exact same structure as the original. You can rename these B's to A, so these are dummy indices again, and therefore you have proven that this thing with the indices fully contracted is an invariant of your theory. So once again, you could build a Lagrangian Lagrangian term in this way. So now an important also result is that the anti-fundamental or complex conjugate, as we introduced above, representation can be obtained as a contraction, and this is going to be very important also in the Young Tableau that we are going to start looking in a few minutes. It can be obtained as a contraction of the Levi-Civiter with a tensor representation with fundamental indices. So in essence, what you can do, you can pick up the fundamental and build the anti-fundamental. In fact, the fundamental is, in a way, I think it's also called the defining representation. And you can build every group representations from the fundamental one. It works like in quantum mechanics. You learn that you can start with the spin 1/2, something like that, and you can use ladder operators to go to other angular momentum representations. So this, in fact, is analogous to that. You start with the fundamental representation and using ladder operators, which are given in terms of epsilon tensors and other things. You can construct other tensors of your symmetry, and also, of course, contracting tensors with other tensors. You build new tensors of your symmetry. So, for example, the anti-fundamental. You have the anti-fundamental that we defined above with one index here below. Now look, you can say I have another chi, but with n-1 indices. Another representation with only fundamental indices, b1, bn-1. So now we can make use of this invariant of the theory, epsilon, to contract this b1 to bn-1 indices here, and it leaves us with a free index. That's why you have this psi a, and this is, by the definition, this is the anti-fundamental representation of your symmetry. And chi is not fundamental; it's n-1 fundamental. Let's say it's a n-1 rank tensor. So this is quite interesting because you will use this in different contexts, as you will see. So in essence, you can also see that this is indeed a group. It transforms as a Exactly. So what we want to prove now, is that this psi a defined in this way transforms as the complex conjugated representation or the anti-fundamental. Recall what is that? So we go above again. It's here. So it has to transform in this way. Let me copy this. So it has to transform in this way here. So let me put here, but smaller. So what we want to check is that this transforms in this way. Let me make here a separation. Right. So this is what we want to prove. So let's start this this proof. So pick up the epsilon that is here and the chi with n-1 indices. So in fact, the transformation properties will be associated to this chi thing. So now this chi transforms in this following way. So this is the chi prime. So it's only fundamental indices. So you have U's without star and B and C below like this, where you now rename this to C. And epsilon, so this in red, this identified what we know is the transformation of epsilon. So we have epsilon E, D1, Dn-1, and now you have UAE, but it's not United Arab Emirates. Here it's really a transformation matrix. You have then the other U star D1, D1, Dn-1, Bn-1, and so on. So these red things are put together here. Now, what you do in the following line? Now you stack together the U's that have a common index. So this V1 is contracting this one. Once again, Osvaldo. So this is how you the summation convention. So guys, it's always there. The summation convention. Bn-1 is with the Bn-1 there. And you group the things in such a way that you get deltas, which you know are invariants of the symmetry. So you don't need to study their invariants. You know that they are invariant of the symmetry. But because of this extra index here, there is one. So this UAE is left outside. So this is how it looks like after putting the deltas there. And of course, now what we do, because of these deltas, you rename all these D's in terms of C's. So you get epsilon E, C1, Cn-1, C1, Cn-1 here, which is equal, and by the definition of the transformation, it is equal to psi E. So this is the anti-fundamental one, and you have this transformation property here. So once again, let me paste here what was the result that we put in the beginning. So you see it transforms in this way, as it's here. So we have proven that indeed this transforms has the complex conjugated representation or the anti-fundamental representation. So in general, what we have, and this is now something very, very, very important when you are building Lagrangian. So I'm calling your attention to these things because this is really crucial. It's, of course, it's in model building, you deal with these things every single day. But it's also important for you to, even if you are an experimentalist or if you are from gravity, you will at some point deal with potentials, Lagrangians, and so on. And it's important to have these things in mind, to know what you are building. So, but in general, what we have is that free indices, that is some indices that are not summed over, determine the transformation law for a given tensor, as you've seen here. So there is one free index here, which is A. It's not summed over, so you see here. So the transformation. So if you were to block, now I was blocking with my hand. Of course, you don't see my hand blocking here. But if you were only seeing this object there, you would immediately know that, okay, there is only one free index, one index that is not being summed, is A, and is an anti-fundamental. So the resulting representation of this one here will transform as an anti-fundamental. If, for instance, you had 2, this would transform as like 2 anti-fundamental representations, and so on. And this is what is written in this green sentence. So tensors, on the other hand, with no free index, and will be invariant under SUN. This is very important because this is what is relevant for the construction of Lagrangians. So basically, in Lagrangians, we don't want indices, free indices hanging around without being summed. You define your symmetry, SU2 cross SU3 cross SU1, or SU5 or SU6 or whatever, and then you look into the representations of this symmetry, and to build a Lagrangian, you need to have all indices of the tensors that you want in your theory to to be contracted or summed over. Of course, there are an infinite tower of representations that you can build, but as you grow in the dimension of this representation, as you have more and more indices of this in these tensors, you have more and more dimensionality there, which means that you will have more and more particles. So of course you don't want to go all the way up to infinity, because as for now, what we know about nature is that there is a finite number of particles that we know of course. Right. So you have seen here that what we need to know and what we need to master are the contractions among tensor indices. And that becomes extremely cumbersome, really extremely cumbersome, and prone to errors every time you do it, if you don't have a generalized or a more diagrammatic way of doing this, which on its own, to understand that this diagrammatics, it's a course on its own, but we'll only use the rules that come out of those developments. Of course, for SU2, you don't need this approach. It's easy. Even SU3, for the lower representations, it's fine. And also in SU2, I mean the lower representations. But if you start wanting to have bigger representations, you would start to need to look into this prescription that we are going to introduce, which is the Young Tableau. Right. So let's then start with the Young Tableau, which is really, if you follow, this is almost like a game. Like, I will give you a set of rules, and you will play. I was even myself having fun yesterday, getting several contractions of indices using the Young Tableau. It's really fun. But first, we need to know the rules. And once we know the rules, which are not difficult, you can list them. And every time you build, you look into your list of rules and you make sure that they are all being respected. You can very easily construct tensor products and know the dimensionality of those representations that we will build. So let's go down to business. And now you notice I have put this in a landscape now. Let's see if it works better in landscape. So now, what is the goal? So the goal is to determine the irreps. Remember, irreps stands for irreducible representation. So it's determine the reps within the group tensor products. And what do we mean by this? So first, we focus on representations with fundamental upper indices. And then indices can be lowered with the Levi-Civita tensor or metric. Levi-Civita, in fact, is a metric of a certain SUN. So a metric of SU2 is the epsilon ij, and of SU3, it's epsilon ijk, and so on. At least for SU2, it really works as a metric. And I think you have seen that for the case of even for the case of spinors, you can lower the index because the Lorentz symmetry has has SU2s in it, and you can lower indices with epsilons, lower and raise them. Right. So so a two-index tensor. In fact, now let's take, this is the simplest example of what we want. So now first let's set up the stage of what we want and why do we care about it. So we have a two-index tensor psi AB that can be decomposed, this tensor, in a symmetric and an antisymmetric parts. Here. Right. So you write psi AB as a symmetric part, so S stands for symmetric, and an antisymmetric, so with the minus here, standing for antisymmetric, and plus standing for symmetric. Where each one of them is defined in terms of psi has, so this is a combinatorial factor here, in this case it's 1/2. So the symmetric part is psi AB plus psi BA, and the antisymmetric part is psi AB minus psi BA. So this is how to define the symmetric and antisymmetric representations of this tensor, let's say. So the transformation properties, now let's look, because there is an important result here. So we have this psi AB, the plus or minus. This goes to a certain psi, which we are calling tilde here. And now you know how does it transform. So this transforms under, you can put a UAC, UBD, psi A DC plus or minus here. Now, if you flip the D and C indices here, the D would see not only here and there, so the indices are dummy along this flip, so you get exactly the same thing, but with renamed indices here and here. But now, if you flip back only the indices of this DC here, so C goes to D, but keep these ones in the same order as above here, you will get a plus or minus sign, here, plus or minus sign here, which depend on whether you are picking up the symmetric or the antisymmetric parts. So the thing is that a psi AB will transform either as a symmetric or antisymmetric tensor. I mean, an antisymmetric tensor transforms, let me zoom out. An antisymmetric tensor transforms into an antisymmetric tensor, and a symmetric tensor transforms into a symmetric tensor. Which means that the psi plus and psi minus form invariant subspaces. Therefore, we can say that the psi AB is a reducible representation, while psi AB plus minus are irreducible representations, because they and this is coming from something that we have seen in the first lecture. That what is a reducible representation? Is so R is reducible if and only if there is a subspace U containing V left invariant by group transformations. So you have this R belonging to U, or this represents RU, this operation here where the U belongs to this subspace U for any group element here belonging to the G, to a group G. So, but if there is no such U containing V, then this R is said to be irreducible, and you defined as an irrep of G. And these are really the relevant representations in particle physics. What we build a Lagrangian based on irreducible representations. So what we really want to do is to look into the symmetrization properties of n by m tensor of under a given symmetry. So that leads us to this to a certain theorem. So because note that this is a simple case with only two indices, but in general, you can have many indices, and you can have them fundamental, anti-fundamental, and so on. So when you want to find irreducible representations, what we want to do is like looking into permutations of indices, essentially. So this is what we are doing, permutations of indices, and looking into the properties of such a permutation. And that there is a theorem that relates the permutation group to SUN groups. This is a known. Actually, I have here referenced for a book where this is demonstrated. I didn't see. I can give you the reference of this book at some stage. But the thing is, the result is this. So every p particle state, so we have a state with the p particle state that both belongs to an irreducible representation of the permutation group and is built up from single particle states of an n-dimensional SUN multiplet, transforms under an irrep of SUN. Let's make things concrete. So this p, first of all, is not equal to n. It can go up to n, but it doesn't have to be n, because in a given tensor with several indices, the symmetry and anti-symmetry properties are not necessarily among all indices themselves, like the Epsilon tensor, which is totally anti-symmetric, or delta, which is totally symmetric. So in fact, the group representations, the irreducible representations, can be anti-symmetric in some indices and symmetric in some other set of indices. And this is what we need to know. And then what this is saying is that the permutation properties among the symmetric indices, so p symmetric indices and q anti-symmetric indices, will give rise to, this is the same as here in A and B. So we have a subspace of representations, the symmetric and asymmetric part. So we can separate those representations and find the irreducible ones by a one-to-one mapping of the SUN group and the SP, the permutation group. So you can think of group representations basically as a set of rules for permutations of tensor indices. Basically, this is what leads to anti-symmetry, or symmetrization, which is equivalent physically. We are talking about how particles transform into each other, or basically how do we permute a particle within a given state, and what that leads towards. So this is a map, let's say. So we have SUN irreps, which are in a one-to-one correspondence with the SP irreducible representations. And we can map, and this is now a result that I'm already putting here because we don't have time to study the symmetry, the permutation group. Of course, in a full group theoretical lecture course, we would first study the permutation group. But we can map these SP reps into Young Tableau. And of course, because of this one-to-one correspondence, we also have these SUN groups that can be mapped into the Young Tableau. And this is what we are going to use. So let's make things more concrete. Consider an index with p fundamental indices. So they are all here above. And now consider the numbers. Maybe we'll digest this better at home, but consider these numbers. So some P1, P2, all the way up to PS, such that the sum of these PIs is equal to P. This is to say that we can build, you can split this tensor into different groups of indices. So first, the green group that goes from A1 to AP, then a second group that goes from AP1 to AP1 plus P2, and a third group that goes from AP1 plus P2 plus 1 all the way up to AP. So in fact, I can even write here I need to pick the same color, which is maybe this one. Just to make things a little bit more. P1 plus P2 plus 1, and this goes all the way up to AP. Right, and this can be represented as a Young Tableau in this way. So look at the colors. So we have the first group of indices, A1, A2, AP1s on the first row. Then you have the red indices on the second row, and then you have these purple indices. Let's say, okay, here this is only on the last row. It's only one of them. So I will, in fact, go back to what I had there. I will put here AP. I will still keep the dots just for if we have a different generalization of it. But this Young Tableau, what does it mean? Basically, in the first line, I will introduce these rules. They will be show up organized below. But what is happening here is that in each row, the indices are symmetric. So any permutation of green indices is a symmetric permutation. Any permutation of red indices is a symmetric permutation. Any permutation of would-be purple indices is a symmetric permutation. But on the columns stand for anti-symmetry. So this is, now there is not a color correspondence here, but A1 permutation with AP1, AP1 plus 1 and AP. So A1, AP1 plus 1 and AP. The permutation of these three indices, and eventually some other ones in between, is antisymmetric here along this column. The permutation of A2 with, here I can explicitly write, with A, it would be A P1 plus 2, it's antisymmetric permutation, and so on and so forth. So permutations in columns of the Young Tableau are antisymmetric. Permutations along the rows are symmetric. So, but what are the rules? And these are the zeroth rules. So the first ones. We first need to build this Young Tableau that you see here. And you see this is left justified, the Young Tableau. So this is the first thing. Young Tableau is a diagram of left justified rows of boxes where any row is not longer than the row on top of it. So we could not have, for example, this thing here. This would be a forbidden Young Tableau, having more rows. So if I want to be slightly neater, this would be wrong. This entire, they cannot be longer. And the same if it was below. But this one would be an allowed Young Tableau. This would be possible. The condition here is that not longer than the row on top of it, but it can be of the same length. So this is the first rule for you to keep in mind when you build Young Tableaus. It's left justified and the length of the rows. So any column cannot contain more than n boxes. And this is because for a SUN group, of course, n boxes, and we are talking here about, of course, about SUN in the context of SUN. So if it's SU2, the maximum length of the column is 2. If it's SU3, is 3. If it's SU5, it's 5, and so on. And we will see this in more detail. So this is the second rule of the first set of rules. So any column with exactly n boxes can be crossed out since it corresponds to a singlet representations, and this we will explicitly see, and this is something that we'll clearly understand. But columns that have, so for example, if you are talking about SUP, an SUP symmetry, this column here with P indices would be singlet. So you could remove it from the Young Tableau, in fact. So any Young Tableau which respects the rules above corresponds to an irreducible representation of SUN. So when you have these three conditions of this set of rules, number 0 fulfilled, you have an irrep of SUN. So now let's come to rules 1. So you may already guess that I only wrote rule 0 after writing rules 1. This is what I have already mentioned above, and that's why I'm putting here again the Young Tableau. So swapping green indices in the same line, we have symmetric. So the tensor is symmetric on the indices along each row, and anti-symmetric indices appearing in the same column. So here actually this is in red, but there is not a red correspondence with this row. Just bear that in mind. In fact, I should have used, if I use a different color, let me try to see if I can modify the color to, it changes the color of everything, but I can do like this. I can do like this. Oops. So just for, oops, no. I just want to avoid some of you by accident confusing it. So blue standing for the blue of the Young Tableau boxes, let's say. So example here, this is an example. If you here we are flipping a 1 with a P, and you get a minus sign because they are on the same line, on the same column. And here you have below you are flipping two indices. So a P1 with a 1 here, P1 with a 1, and this it's a plus sign because it's symmetric in this interchange of parameters. Now, to compute the dimension of a representations, we need to consider another tableau, which is based on the Young Tableau, but is what is called the standard tableau. This leads up to the second set of rules. So this is for your exercises, this is what you will need. You need to look into these rules and apply them. So the standard tableau corresponds to inserting indices 1 to n in the Young Tableau boxes such that, so you first draw the Young Tableau following the rules above, and then to build the standard tableau, what do? Insert indices from 1 to n such that indices do not decrease. They can be equal, but they do not decrease from left to right within each row. Indices increase, so they cannot be equal, from top to bottom in each column. If the number, and then you build all such possibilities of combinations of 1 to n that respects A and B, and the number of standard tableau that you construct yields the dimension of the representation. For example, SUN, what we have in this table. So fundamental representation, only one index. You write only one box. So the standard tableau are all boxes that you can write. So it's if it's SU3, you have 3 boxes. The fundamental representation is 3-dimensional, and this is indeed, so n equal to 3. This is indeed what you have. You have 3 quark colors. The fundamental representation is 3 quarks: red, green, and blue. That's the quarks are in the fundamental representation of SU3. SU2, for example, the fundamental representations, n equals to 2, so you have one Young Tableau blocks. It's exactly the same, but when the standard tableau are 2 of them, so we have 1 and 2. And that means that the SU2, the fundamental representation of SU2, has dimension 2 because you can build 2 standard tableau out of that. Now, if you have a symmetric n by n, so symmetric, 2 indices are symmetric. So you build a so it's two boxes as you see here. And now you number these boxes following the rule. So rule number A here, the indices do not decrease from left to right. So you can write 1, 1, 1, 2, 1, 3, 1, 4, and so forth, 1, n. And then 2, 2, you cannot write 2, 1. So if I have something like, oops, I don't want to mess up this. If you want to write something like, let me put here I will put them in small. If you have something, for example, like 2, 1, 2, 1, this is not possible because this does not respect rule number A. So rule 1A, let me just put this slightly smaller because this is just a side comment. So it would violate this. Indices would not do not decrease from left. Indices would decrease from left to right. So 2 is decreasing to 1, and this is what we don't want. But we don't have rows, so columns, I mean, so this is not yet here. But it comes about if you are talking about antisymmetric. So an antisymmetric AB tensor would be a column, as you can see here. And now you don't have anything to do with this rule 2A. So do not decrease from left to right does not apply here because we only have one column. But the B rule would apply. So indices have to increase from top to bottom in each column. So this is, you have 1, 2. You cannot have 1, 1. 1, 2, 1, 3, 1, 4, 1, 5, 1, n. Then 2, 3, not 2, 2. 2, 3, 2, 4, 2, 5, and so on to n. 3, 4, 3, 5, 3, 6, and so on up to, well, this is just like something like, yeah, this is the last, by this order, this would be the last element, n minus 1, n, with all other possibilities there. And once again, a forbidden possibility would be something like if you would have, for example, when you pass, you go to 2, 2, 1 here would be forbidden. So this is also not possible here. So let me make this smaller. Right. And of course, you can generalize it for symmetric and antisymmetric tensors, but symmetric tensors would have several boxes. So this would make this process a little bit more cumbersome in terms of the standard Tableau. And antisymmetric is simply columns. And of course, you can have combinations of both. As the example here, this is a combination of both. Here you have both columns and rows. And this is indeed the final goal, is to get to this type of tableau. Right, now let's put our hands dirty. That is, let's leave this abstraction and let's go to concrete examples. SU2, let's start with SU2. Fundamental representation of SU2. The Young tableau is simply a box, as we have agreed already. There is only this index, there is one box. What are the standard tableau? The standard tableau, it's 2, as I said. So the dimension is the number of standard tableau that we can count. So this is a doublet. Anti-fundamental representation. Now look that you build, as we have discussed above, I think you remember, the anti-fundamental representation can be built from the fundamental representation using the Epsilon ij. But here, this is again built up only from one index. So this is also a doublet, and it's a pseudo real. So it is represented exactly in the same way, with only one box. So it's also a doublet. In fact, it corresponds. So it's pseudo real once again. But what about the singlet representation? So if you have a column, this is what I said above. Look at this. The maximum in one of these rules. Any column with exactly n boxes can be crossed out since it corresponds to a singlet representations. We'll see it several times. And now this is the first time we will see it for SU2. SU2, n equal to 2. So this is n, we know. Let's see, of course, let me write the obvious here, but n equal to 2. So we have two boxes. So this is the Young Tableau and the standard Tableau. So white here stands for Young Tableau and ST stands for standard Tableau. So following the rules, so that is in the column, the numbers must grow. So the only possibility is 1, 2. And we only have two indices because these indices only go up to 2. So we only build one standard Tableau. So the dimension is 1 and it confirms it's a singlet. This is a singlet. What about if we write this Young Tableau with two boxes with symmetric indices? So we go to the standard Tableau and we have the numbers have to be equal or larger. So the numbers cannot decrease from left to right, cannot decrease. So they have to be equal or rather increase. So the possibilities is 1, 1. Second standard Tableau is 1, 2. And the third one is 2, 2. So 1, 2, 3. This has dimension 3. This representation. It's a triplet. And what do we conclude about the triplet already? We conclude that the triplet is symmetric under their indices. So it's symmetric under transformations of both indices when you flip them. So you can, just in a more intuitive way, you can write the doublet, you know, so it's this box as we have verified. So this is a psi I with two components. For example, you can write the singlet, and I think this is also familiar from in quantum mechanics. When you have addition of angular momentum, you build like the singlet states, triplet states, and you can have this. For example, the singlet is this anti-symmetric. So look, it's anti-symmetric in these two indices. So it's psi ij with anti-symmetrization, which is equal to psi1 2 minus psi2 1. This is the anti-symmetrization property. But the 3 is symmetric under the 3 indices, so they can be both equal. Here you cannot have them equal. That's why it's a singlet only one possibility, because if they are equal, this would be equal to 0. So this is a singlet, only one entry. It's as if it transforms as a scalar, let's say, under SU2. This is a triplet because you can have 1, 1, you can have 2, 2, and you can have the symmetric counterpart of the singlet, the psi1 2 plus psi2 1. So this is in the sense that this is a triplet. I am doing this for you to understand the box structure and what's going on here, and in this index structure, because this is still easy to do for SU2, but of course becomes increasingly cumbersome if you start to write these states in terms of SUN, larger representations. Now SU3. Let's do the same procedure for SU3. The fundamental representation, again, it's a box. Now n is equal to 3. N is equal to 3. So we are going to write the standard Tableau, and we can have 3 standard Tableau. One with 1, another with 2, another with 3. And here there is no indices to grow left to right or to grow top to down, because this is an isolated box. And the standard Tableau is the combination of all possible Young Tableau filled up with indices. So we have 3 of them, so the dimension is 3. That's why the fundamental representation is a triplet. So once again, we are seeing, as like in the case of quarks, they transform under the fundamental representation of SU3 or even anti-fundamental for anti-quarks, and they are all triplets. Speaking of anti-fundamental, not yet anti-fundamental. First, let's look into this. We have two boxes, symmetric under indices A and B. Build the standard tableau, and now want to fill this standard tableau with numbers from 1 to 3. So 1, 1, 1, 2. This is allowed. Now 1, 3, 2, 2, 2, 3, 3, 3. These are all possible combinations following the rules above. Dimension is 6. So it's a sextuplet or a sextuplet. This is how this is denoted. What about the anti-fundamental? For the anti-fundamental, note the following. Pick up this representation, like the sextuplet, let's say, with the two indices, and plug the Epsilon tensor. This is what we have done above. We said we can build a fundamental representation with an Epsilon tensor and n-1 dimensional representation. And this is what we are doing here. We know that this psi A transforms as the anti-fundamental. But if you look at the indices structure here, there is like these B and C that are anti-symmetric in the sense that it can be constructed from a symmetric rep and the Levi-Civita tensor. So if you flip this B and C here and B and C here, you get a minus sign. And in fact, what is this? The possibilities you can have these three possibilities where you have psi 2 3 minus psi 3 2, psi 3 1 minus psi 1 3, and psi 1 2 minus psi 2 1. It's just filling up here indices 1, 2, and 3, and then the B and C accordingly for the non-zero entries. So this must form an anti-triplet because this is the anti-fundamental. So in terms of Young Tableau, we have these two things here. So two boxes stacked on top of each other, which has only three possibilities. The numbers have to grow in columns. Remember that numbers have to grow in columns. So it goes from 1, 2, 1, 3, and 2, 3. So you count the number of standard tableau, you have 3, and you have an anti-triplet, right? Now, what about this representation? This has exactly n boxes. So I said, if it has n boxes, this is a singlet. Let's see if it's indeed a singlet. What are the only possibilities following the rule? Indeed, 1, 2, and 3. There is no rows to grow the numbers, and the numbers have to grow, and they cannot be. So the number below the first one has to be bigger. It doesn't have to be consecutive, but it has to be bigger. And because of not being having to be consecutive, if n was like 4 or 5, you would have more possibilities of 3 columns. But in SU3, a column with 3 boxes only has 1 possibility. So the dimension of this representation is 1. So this is a singlet of SU3. And this is what you do when you contract quarks with color and anti-color. This is what it leads to. It's to this representation. So you could even write this in a so this singlet in a more so if you still like to see these states, you can put the A, B, and C indices. So A and then B and C here. So B and now anti-symmetrization in A and C, and now the same with A and B here. And if you have a permutation between A and C, this goes to minus A. So in general, for SUN, there is only one way we can organize n particles in an n-dimensional, totally antisymmetric state. We are talking about a totally antisymmetric state. Up to transpositions that must change only the sign. So you do transpositions, it changes the sign, but it's only one possibility of organizing this state. So in SUN, such a rep is always one-dimensional and is said to be singlet. So in general, you have this for SUN groups. So for SUN groups, A column with n entries is a singlet, always. What about the adjoint representation? So we know from what we learn above on the algebras, we know that the dimension is n squared minus 1, which is equal to 8 for n equal to 3. So let's look into this Young tableau. We'll learn later on why is this Young tableau, which has 2 symmetric and 2 anti-symmetric indices. And let's build the standard tableau. So what happens? Numbers must not decrease in rows and must increase in the columns. So in the rows, you can have 1, 1, 1, 2, 2, 2, and 2, 3, as well as 1, 3. In the columns, we need to have 1, 2, and 1, 3. We can only have columns with 1, 2, and 1, 3. 1, 2, 1, 3. Also 2, 3, of course, and 1, 2, 1, 3 again. Never repeated indices. But in the length, in the rows, you can have 1, 1, 1, 2, 2, 2, 2, 3, and 1, 3. And all possible standard tableau that you build here, so you count them, and this gives rise to 8. So the dimension of this Young tableau is 8. So you have an octet. So in essence, for SU3, these are the simplest representations of SU3 and the most important one. The sextuplet is not often used. Okay, it's used, but not often. The most important are indeed the triplet, the anti-triplet, the octet, and the singlet. So what is a color singlet? So a Lagrangian term with between 2 quarks and a gluon, for example, it can form a singlet. Or an electron is a singlet of SU3. What is 3? Is a triplet. A quark, any quark is a triplet of SU3. Any anti-quark is an anti-triplet of SU3. And octets and the gluons. That's why you heard there are 8 gluons in the standard model. There are 3 quark colors and there are 8 gluons, because in fact this is like not 8 colors because there are only 3 colors, but is 8 non-singlet combinations of color and anti-color. There is one color combination that is, in the same way, guys, think in the same way as you did for this spin. This is the same. 3 is the adjoint of SU2. If you say there are 2 colors, SU2, 2 colors, so red and green. I prefer green and red because I like green ahead of reds always. So green and red. Then you have one combination that is a singlet and one combination that is a triplet. Right? So you can have green anti-red, red anti-green, which would be this one. Sorry, red anti-red and green anti-green. Exactly. And then the other one, this one would be green anti-red, but in a symmetric way. And this would be green anti-red, but in an anti-symmetric. Well, actually the 2. Green anti-red minus red anti-green. And this would be green anti-red plus red anti-green. And this would form a triplet. But we have 3 colors. So SU2, this works fine for weak charges. It's the same mathematics. But for colors, that is what we were talking about. We have 8 colors. Of course, I'm not going to spell out now all. So these 8 colors. I'm not going to spell out now green, anti-blue, red, blue. There, you can build them. You can find 8 combinations, and then there is one singlet combination, which is I think is green anti-green plus red anti-red plus blue anti-blue, and there is the okay, an written in an anti-symmetric way or some other combination there, and another one with the plus signs for the octet. So, but now you may be thinking at the moment, I'm in trouble if he asks me to calculate the dimension of something with a plethora of boxes. in fact, indeed, if you grow the dimension, the number of boxes, using the standard Tableau, it becomes also rather cumbersome. It's better than just putting the tensors itself and looking at possible contractions and symmetrization and anti-symmetrizations. If you use the tensors directly in generic SUN, you will almost 100% sure screw and getting representations that are double counted, and getting representations that that violate the symmetry somehow, forgetting other possibilities that will happen almost for sure because we are humans. Also, computer will take longer. A computer with a young Tableau algorithm in it works a lot faster for this. But using the standard Tableau helps a little bit in the beginning, but also becomes cumbersome when you go to more generic and larger representations. So this leads us to a new definition and a new set of rules. In this case, it's the hook rule. First, let's define what is a hook. For each young Tableau, a hook is a line that comes in from the right, passes through the center of some boxes, and at a given box turns downwards, exiting the Tableau at the bottom. Okay, at this time, this is complicated to digest. Let's look at an example. This is a hook. This is the hook here. The hook is basically where it turns, but for every single box, you can draw a hook. So this was drawn for this one. You can draw a hook here. You can draw a hook there. You have a hook here. Recall that it's a line that comes in from the right. So it comes in from the right. You can put here some arrow. So it comes in from the right. Oops. Here comes in from the right, passes through the center of some boxes. In fact, so passes through the center of this box, of this, this, and that. And at a given box, in this particular case, at this box, turns downward. So it goes down, exiting the Tableau at the bottom. So exiting the Tableau here. Enters here, passes through these centers, and exits here. This is a hook. So, and there is one hook per box in any young Tableau. So there is a hook here, as I was saying, a hook there. The hook of this one would be like that. Another hook here, another hook there, another big hook here, another hook here, another here, here. So I'm drawing actually whole hooks as I speak.
So there are as many hooks as there are boxes.
Exactly.
Right? Yeah.
Exactly. There are as many hooks as there are boxes. But each hook passes through a different number of boxes. And that's the point. There is one hook per box in any young Tableau. Osvaldo, there you go. And we can assign to each box the number of boxes that the hook passes through. So for example, here in colors, the green one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number 10 there. Now this blue one passes 1, 2, number 2. This purple one, it's only one. The red one above, so 1, 2, 3, 4, 5. So number 5 here. Now this also dark purple, 1, 2 box. So this here. This one, 1. And you do the same for all the other ones, and you fill in the numbers in this young Tableau. This is a rather generic young Tableau, and you fill in these numbers. But why do we want these numbers? We want to calculate the dimensionality, and these numbers will be related to that. This hook, don't ask me how, because I have no idea. I just know it's a known result. But this, of course, follows from rigorous theorems and of the permutation group of this SN group. And this is demonstrable, of course. I just don't know how, but it is. This is at least what I read in books. So the product of these numbers. So now we multiply all these numbers, 10 times 8 times 6 times 5 times 2 times 7, 5, 2, and so on. And this gives something that is the hook factor. So the hook factor is the product of all of those. So I'm putting here also the ones just for, so you have 4 ones here. So 1 to the power 4. You have 4 twos, 2, 2, 2, 2, 2, 2, 2. These 4 twos, 2 to the power 4, 1, 10, and so on. So this is just multiplying all of them. And now there is another definition. That is, the dimension of a SUNY rep is given by P over the hook factor. And what is P? This is what we need to know. So H is the hook factor, and P is obtained in the following way. Again, from such theorems that I was mentioning. So to obtain P, we need to look into another set of rules. So we draw the Young tableau for a certain SUNY rep. Let's consider the Young tableau above. So in the upper left box, we write a number n, which is equal to the dimension of the symmetry that we are talking about. Now we increase the number in each box by 1 when you go to the right. So this means increase the number. So if you have like 1, then you have 2, 3, 4, and so on. And you decrease the number by 1 when you're going down. So sorry, I did something very wrong here. If it's n equals to, if it sets you 3, for example, you have 3. In the next box, you have 4, 5, 6, all the way up to infinity, if you have a huge one. But going down, you have to decrease the number. So it 2, 1, and you cannot have more than below 1. 4, 3, 5 would be 4. And this could be a Young tableau like this. Now just putting boxes here. So decrease 1 by 1 when you go down. So this is an example. So for example, here you have one thing that you get is that at least you need in this case. So you have 6 boxes here. If I'm not putting here dots, this means that the n minimum is 6 for this Young tableau that we've been talking. So if n is equal to 6, so if n is bigger than 6 or above, this is the P factor, is the product of all of them. So you see, you have n to the power of 3, which is here. We have n minus 2 to the power of 2, n minus 2, n minus 2, n minus 1, n minus 1, n cubed, n plus 1 cubed, 1 plus 1, somewhere here, 1 plus 1 plus 1, and so on. So this is just a matter of counting. So if this is an irrep, example of SU6, the dimension would be, so on the numerator, we have this P, and this would be changing n equal to 6. So you just replace that, and it gives the numerator here, and the denominator is the hook factor. So for the hook factor, it's just the product of all of this. So I'm using, this is the same for SU6, for SU7, for SU1000, for anything above SU6 with this example of Young tableau, because it's the number of hooks. So it has to do with the permutations and the combinatorics there. But this depends. So these numbers here depend on the group. And in this particular case, if this is a representation of SU6, this would be a huge representation, and 19,404 plets. That means you would have, in this case, 19,404 particles. If you split this SU6 into well, of course, if you have into SU3 cross U1, you also would have quarks in there, or something behaving as a quark, which also has three colors. So if you count the number of colors contained inside the SU6, you would have 19,404. Definitely, this Young tableau is not something that when you build a model, you don't want immediately to start with these representations. But here, this is simply a mathematics exercise. So concrete examples to finalize. So for SU2, so you have the doublet, the singlet.
Sorry,
and the
I have a question about the previous slide.
Yes.
So, but when we create this table, do we have so the shape of the tape of the tableau is it fixed because we're always using the same, but could we have just something that's a row and then we just have n
Yes.
factorial?
Exactly. You can have, it depends on what is the representation that you are taking care of.
But if there is such a representation where the p factor is just n factorial.
Yes,
Okay.
exactly. If it's a column.
Yeah. Okay. Thanks.
If it's a column, and that's the case of two cases, either the singlet or the one just before the singlet. We'll see it right now. I mean, here in SU2, this is p factorial here.
Right, yeah.
Look, for the doublet. So now we are not going to do the standard Tableau. So we have the hook. There is only one hook passing one box. So the hook factor is 1. And we have, we need to start with the largest number. Recall the rules. The rules are here. Rule 3. Draw a young tableau for a certain. Then in the upper left box, write n equal to n. So what is the upper left box of a single box? Is itself. So you write n equal to n. So you write 2. Dimension is p over 2. Let me just recall. So d is p over h over the hook factor. This is generic for any SUN. So this is 2 over 1, and it's 2. Yes, it confirms us. It's a doublet. Now what about the singlet? Look, this is your so it's p factorial in both ways. So the hooks. So the green hook passes through 2 boxes. The red hook passes through 1 box. So the hook factor is simply 2. P is your p. In this case, for when you have only one column, is always p factorial in both cases. Sorry, not p factorial, n factorial, Oswald. Here. So 2 times 1. So again, d equals 2 over 2, p over h. Singlet. Perfect. Triplet. You have 2 hooks for the hooks. 2 hooks here and 1 hook there. So again, the hook factor is 2. But now let's go to the rules. Increase the number in each box by 1 when you go to the right. We are now going to the right. So while going to the right, we increase the number. Sorry, I'm already in P. 2 and 3. So P equals 2 times 3. So D equals 2 times 3 over 2, which is 3. So confirms in a much simpler way than writing the standard Tableau. What about SU3? Let's confirm these possibilities. So we have for the triplet, again, 1 hook and n equal to 3. So P over H equal to 3. Confirms. 3 bar. 2. So green hook has 2 boxes. Red hook, 1 box. Hook factor is 2. Now we start n equal to 3 times 2. So this is 3 times 2. Again, it's 3 factor. Well, it doesn't have the 1, but it's the same as 3 factorial. Technically, it's not 3 factorial, but it's equal to 3 factorial. So D equals to 3 times 2. So it's P over H over 2. It confirms. So it's 3. So the anti-triplet is also a dimension 3 representation. What about the octet? So now we have two symmetric and 2 anti-symmetric indices. What about the hooks? The blue hook goes over 3 boxes, 1, 2, 3. So we put the 3 here. The green hook, 1 box, so you put 1. The red hook, 1 box, you put 1. So the hook factor is 3 times 1 times 1. I can write here just for 3 times 1 times 1. For those that are seeing this for the first time, it can be relevant. Now the p factor, we start with 3. Now we need to go to both rules here. You have to bear in mind these rules. increase the number in each box by 1 and decrease the number by 1 when you go down. So let's do that here. Start with 3, n equal to 3. Sorry, 3 here, 3. Increase when you go to the right. So 4, 3 go to 4. And decrease when you go down, 3 goes to 2. What is the p factor? It's 4 times 3 times 2. So d is 4 times 3 times 2 over 3. This is 8. Right? So you just eliminate these 3's. 4 times 2 equals to 8. So octet confirms. What about the 6-plate? The hooks, it's 2. So 2 hooks, 1 goes over 2 boxes, another one over 1. And the p factor is starting 3 and grow 1. 4 times 3. So now it's 4 times 3 divided by 2. 6 works. Again, what about the singlet? So this is where the hook factor and the p factor is the same. It's indeed 3 factorial. So this is 3 factorial, 3 times 2 times 1, because of 3 hooks. 1 hook that goes over 3 boxes, a hook that goes over 2, a hook that goes over 1. And then the rule of decreasing the numbers in the column, 3 to 1. So it's 3 to 1 over 3 to 1. Dimension is equal to 1. Confirms. In fact, and here is what I say, for any SUN, the dimension of a column with n boxes is always n factorial over n factorial, which is equal to 1. And this is why we can remove this from Young Tableau and immediately get a singlet there. Right. So this is it for filling out a Young Tableau and computing their dimensionality. I think you must be tired for now. We would go to tensor products. This is the really important part, but I think this is better to leave for the next one, because I will already start introducing a few concepts of the standard model along the way. Maybe we should stop now. Next Thursday, perhaps already in person. I don't know how is it going to be. I need to ask.
I had
yes.
something to bring up, because we had a class scheduled for the 18th, I think.
For the 18th?
Yeah, so I'll have to talk, because we had a black holes class that was moved from the 4th, and I think we're moving it to the 18th, but I think we'll have to remove it. But I'll keep you updated. You have priority here because it was already scheduled, but I'll have to talk to Pedro Cunha about it.
Yeah, so this SM2 on the 18th.
Yeah,
exactly.
Yeah.
So it's already, this is one of those that is really on the schedule. The one that was scheduled, aside from this, was the one on the 20th. Yes, that was the one that you chose on Doodle, but that one, okay, that one could be.
I'll just have to talk.
Okay. It. Okay, that would be good.
Yeah.
Right. Okay, guys. So I don't know if you have any comments or questions that you want to ask. I don't know next week how is it going to be. I'm not sure if it's allowed to be. Well, in principle it will. If it's there. So so Marco, Osvaldo, and Alexander, would you also Ilaria, but she's not here today. Would you go there to attend the lecture, or would you stay at home?
Yeah, I would go.
I'd go there.
Okay. So if it's allowed, so I just want to know, because if I'm the only one there, that would not be necessary. But if you say that you go, I will. I also prefer to go, of course.
Yeah,
I also prefer. Okay, guys. So any questions or comments?
Professor?
Yes. Alexandra, yes.
About thing that was already mentioned. I have some doubts regarding the take-home exam. I don't know when can I speak to you about that?
Yes. Let's see. Before that, we can speak very fast. about that. But let's see. What Oswald, we talk later about what you said. I think this is a bit more urgent because Alexander is trying to solve.
Yeah, of course. I'll email you. I have a class at 2, but
Okay.
I'll email you and you can set.
And even we have our meetings we don't offer. We can at some point even discuss there if there is some dead time in such a meeting. But anybody has a question about today's lecture? Okay, I will assume that there is no questions, or there will be questions later on eventually, which is absolutely fine. So yeah, I would say, Alexandra, you can we can quickly discuss after this meeting. We just stay in the room unless someone else also has something to say. But yes, I would say that we can discuss a little bit about that.
Okay, thank you.
About that. So your question is, in fact, so your question is about the first exercise, right?
Right.
So in very brief terms, so that that is an exercise where you look into the Lagrangians, and you need to say that L equals to L prime. That's the transformation.
Yeah,
property.
right. That's what I did. Just my question is about the conditions I impose on the parameters and the components of the parameters. They get a little bit extensive for the last transformations, and I don't know if I'm.
They should not.
Yeah, that's the problem, because I wanted, if I could then share the screen so I can show you what my specific doubt was.
Yes, and the other ones can. Well, let's see. I don't want the other ones to see each other solution, because it's.
Yeah. Would you like us to leave? That's fine.
Let me see. I'm trying to see what is the best thing here to do. So all of you can ask questions. I said you can ask questions, and I can discuss with you in the same terms with all of you.
Yeah.
And don't hesitate in asking questions if you have questions. The idea is that you understand what is to be done, and that you learn. But also now showing the resolution is not the best practice here, because it will, at least, I of course I believe that you are all serious people. I totally believe on that, but the thing is that at least it would bias your reasoning, and I want you to get involved alone. And if you have the same question, you ask me, and I tell you exactly the same thing that I will tell to Alexander.
Okay, well, I have to prepare lunch, so I'll just head out anyway.
So yeah, so I would say that Alexander, so you have to you prefer to show, right?
Yeah, it would be easier. I also have class at 2, so I cannot. I have to have lunch now. But if I think it would be easier just show so you can clearly see.
Let me just show something to all of you here before you go there. So I will put here the hand, and then I will erase this before you show, because what you have is like you have something like so you have a Lagrangian equal to some like mu ij phi I phi. I'm not sharing the screen. Before you also let's see if it helps out. So if this is like a Lagrangian phi I phi j, only a mass term, something like this, and if I tell you that there is a symmetry that phi I goes to phi j, then you need to make that L equals to L prime, such that mu ij phi I phi j has to be equal to mu ij prime phi I prime phi j prime. So mu ij phi I phi j equal to mu ij prime, and this would be phi I phi j because they go into each other, let's say, which would tell us, okay, here in this case, this would be simply mu ij to mu ij prime in this case. So simply this. But I'm trying to see, because I don't want to answer the exact same results. I don't know
Yes,
if it.
yes, I get that. Maybe I really have to leave because I have a
Okay,
class at 2
so
and
guys,
I have to eat.
so
And
in this case, I will have the discussion on with Alexandra, and then you guys will be able to join later.
Okay, I'll head out.
Okay, have a good day. Bye.
Okay,
Bye.
you too, guys. You too. Bye bye.
Bye bye.
Bye.
Bye bye.
okay, sorry. I
Ela
can share
pode falar em
so.
português. Deixa-me só parar
Desculpa.
as gravações.
Claro, certo.
Espera aí, agora. Já o ecrã e agora aqui. Ok.